Right, I'll start with the first stats question. So, show that an estimate for the mean weight of the 50 plums is 63.72 grams. So, start by working out the frequency of each bar, because it might be that there is a scale factor at work in this histogram. Remember, the area of the bar is proportional to the frequency. It might not be identical to the frequency. So we need to know the frequencies for each group so that we can calculate our estimate of the mean. So let's just work those out first. Class width of 2, frequency density of 3 gives us an area of 6. Class width of 2, frequency density of 12, area is 24. Class width is 2, frequency density is 8, area is 16. Class width is 2, frequency density is 2, area is 4. Add those all up. 6 plus 24 is 30. 16 plus 4 is 20. Gives a total of 50, which corresponds with the total number of plums we've got. So there is no scale factor on this one. The area of the bar is the frequency. So we can think about this as just being like those grouped data tables that you are used to calculating estimates of means using. So what are we having? Weight. I wish I never did this because that's gonna maybe I'll make the pen a bit thinner for this bit. So the weight 60 is less than or equal to x is less than 62. You don't have to draw this table out yourself if you're answering this question. I'm just demonstrating how this corresponds to something that you might be a little bit more familiar with than what's presented to you in this question, in case that helps anyone. So we're kind of used to seeing those kinds of tables where we've got our variable and we've got a corresponding frequency. I'll just put F. So frequency we know for that first group is 6, 24, 16 and 4. And we know if we are calculating an estimate for the mean, we've got to use the midpoint of each group, and we tend to call that x. So the midpoint of each group we can see is what they've used to draw this frequency polygon. So we've got 61, 63, 65 and 67. And if we want to calculate an estimate of the mean, we use the formula sum fx over sum f, or n you might put on the bottom because the sum of the frequency is our total number. So let's work out what fx is for each of these. 6 times 61 is 366. I'll just put fx at the top there so we know what it is we're doing. 24 times 63, no idea. I'm going to get my calculator out for that one. (24 times 63), 1,512. 16 times 65, 1,040. 4 times 67, 268. So our sum of fx is the total of all those numbers in that column there. Add them all up, 268 plus 1,040 plus 1,512 plus 366 comes to 3,186. We know that our total frequency, or sum f, is 50. Sum fx in that box there. So then to find our estimate, we just do 3,186 divided by 50. And we get the answer 63.72. It's a show that question. We've got the answer there. So if you didn't get 63.72, you know something's gone wrong. Go and have another look. Let's tidy that number 3 up. I don't like that very much at all. We get 3,186. So that's what we're doing. We're estimating the mean from grouped data. It's just that the grouped data has been presented in this form of a histogram. But we can turn it into a table if that's what you're more used to working with. Okay, estimate for the standard deviation. So we know the standard deviation is the square root of the variance, and that the variance is the mean of the squares take away the square of the mean. Okay, so that's how I like to remember it. There is a formula for standard deviation in the formula book, but it's not quite the same as the way we've tended to do it. So if you remember our version, I think that's the version that's easiest to work with. So the mean of the squares means we're going to do the sum of fx squared over n still being the sum of the frequency, take away the square of the mean. The mean was sum fx over sum f, and we're going to square that, and that would be our variance. That's not our standard deviation. The standard deviation is the square root of the variance. Okay, so we need to figure out this top number here, sum fx squared. That is not the same as the sum of fx all squared, because we're not squaring our frequencies, we're squaring x and x only. So we need to square all of our x values and then multiply each one of those squared x values by the frequency. Then we can add them all up together. So I'm just going to make a new column in my table, so I'll get rid of that. We've finished with that now. Okay, so we're going to have x squared this time, and then we'll have another column again for the pen has vanished. There it is. Fx squared. So x was 61 means x squared is 3,721. X was 63 means x squared is 3,969. X was 65, x squared is 4,225. X was 67, x squared is 4,489. So then we need to multiply each of these values by the frequency to get fx squared, which we can then add up to get the sum of fx squared. So our frequency was 6. 6 times this number, 3,721, gives us 22,326. 24 times this number gives us 95,256. 16 times this number, 67,600. And 4 times this number, 17,956. Okay, so let's total all of those up to get our sum fx squared. 17,956 plus 67,600 plus 95,256 plus 22,326 comes to 203,138. Okay, that sounds about right. So I'm just going to check my adding up one more time. 22,326 plus 95,256 plus 67,600 plus 17,956. Yeah, still get the same answer. So fingers crossed that is the right one. That's the only new number we need to plug into this formula. So we want the square root of our sum that we've just calculated over sum f, which is 50. Take away the square of the mean. Well, we've already calculated the mean and we were told what it was anyway in part A. So we don't need to plug all those numbers in afresh. We can just use that value. And bung that in the calculator and we get, let's have a look, 203,138 over 50. Take away 63.72 squared. 1.5879. Dot, dot, dot. That number goes on. So we'll round it to 2 decimal places would be ample. 1.59 is our standard deviation. Okay. Final part. I won't write anything down for this just to save time. Most people got this one because we remembered that when we're doing a coding, that shifting everything up and down doesn't affect a measure of spread, which hopefully is self-evident. If everything is 5 grams less than we thought it was, then a measure of spread won't change because everything is still as spread out as it was before. The mean would change. Yeah, the mean would reduce, but the standard deviation won't change. So the effect this will have, it won't change the standard deviation. A reason for your answer, just as simple as everything has moved by the same amount, is fine. You don't have to go into great reams of detail on this. Everything has moved by the same amount, so the standard deviation won't change, is a perfect answer to that question. All right, so there's the first stats for you.